Alright, to finish notes from 4.4b, this is on second fundamental theorem of calculus, is that we're considering a function where we're considering the definite integral as a function with a constant as lower bound and the upper bound being a variable. So we have a moving right bound. And the second theorem of calculus is essentially showing the relationship between derivatives and integrals. So if I find the derivative of a function that's an integral from a constant to a variable, then the derivative and integral, they basically cancel each other out, but we do have to, but with some slight changes, because the upper bound is a variable that is going to be plugged into the function. So if I find the derivative of the definite integral of a f of t, then these essentially cancel out. So my function is going to remain as is, f of t, but this upper bound will be impacted. So we basically plug the upper bound into the t value, so f of p of x, times the derivative of p of x, which is p prime of x. Okay, so the derivative does affect this p of x with p prime. However, we don't have to, the original function is basically untouched because these two operations cancel each other out. All right, let's look at example 2. Okay. Find the derivative of the definite integral of this function from -3 to x. And this is set up for us to apply the second theorem of calculus. These essentially cancel, these operations essentially cancel each other out. This square root of t squared plus 4 is going to remain pretty much this function. But to follow the rule is we plug the upper bound in for the x, so we get square root of x squared plus 4, multiplied by the upper bound's derivative, so the derivative of x is 1, so we simply have square root of x squared plus 4. Okay. Part B, the definite integral from 3 to x squared, square root of t minus 1, and then find the derivative of that. So operations cancel each other out. We take the upper bound, plug in for the t, so square root of x squared minus 1, multiply by the upper bound's derivative times 2x, so we get 2x times square root of x squared minus 1. Part C, we have to make some adjustment because the upper bound needs to be the variable, and the lower bound needs to be the constant. But here we have it flipped. But we talked about how one of the properties we can use is if we flip the bounds, we can just pull a negative on the outside. So I'm going to rewrite this as the definite integral from 0 to 3x of 1 over t plus 2 with a negative on the outside. So this is set up for us to apply the second theorem of calculus. We plug 3x in for t, so negative 1 over 3x plus 2, multiplied by the upper bound's derivative. So 3x becomes 3, and we combine that to be negative 3 over 3x plus 2. All right, the last example here. Find the definite integral from x to x squared, from x to x squared of 2t plus 3. Here's the problem is that we can't use second theorem of calculus because one of the bounds would need to be a constant. So we have two variables here, so we're going to have to evaluate this step by step. We're not going to be able to use the second theorem of calculus. So we're going to ignore the derivative, and we're just going to focus on finding the integral of this of this function. So we evaluate 2t plus 3. So the integral of 2t plus 3, go through power rule, we get 2t squared over 2 plus 3t. Upper and lower bound being x squared and x. So plug the upper bound in, we get x to the 4th plus 3x squared, so that's the upper bound, f of b, minus f of a, plug x in for the t's, so we get x squared plus 3x. So all this is the result of the definite integral of 2t plus 3 from x to x squared. Now we can find the derivative of the result that we just took. So Now we want to find the derivative of x to the fourth plus 3x squared minus x squared minus 3x. So we go through power rule, go back, and combine like terms, which we get 3x squared minus x squared, which is 2x squared. And then we find the derivative going through power rule, so 4x cubed plus 4x minus 3.